Hi everyone, my name is Corey Green. I'm Javelin's 3D Scanning Product Manager. I'm looking forward to sharing with you a fast, simple workflow merging 3D scanning and reverse engineering. The demonstration portion of this webinar will be showcasing the handheld Artec Leo. It's a portable scanner with an onboard battery and a touchscreen, freeing you from carrying a laptop during scanning. It's designed for parts that are up to the size of a pickup truck. It captures both geometry and color information quickly and easily, allowing handheld scanning to be used in a wide variety of industries, environments, and situations. I'll be reverse engineering the captured data using SOLIDWORKS, with the addition of the GeoMagick for SOLIDWORKS plugin. This is a powerful set of tools for SOLIDWORKS users to easily interact with scanned data files like meshes and point clouds. 3D scanning is unique in its ability to support both reverse engineering and inspection applications. We'll be covering reverse engineering for the remainder of this presentation. However, inspection can take a few different forms. The classic case is inspecting new parts, ensuring that they meet spec. This could be internal or as part of an incoming QC process. Alternately, you could scan and compare tested prototypes to ensure your simulations are accurate. Finally, worn parts can be scanned to quantify the effects of long-term use. On the other hand, many users are looking to scan in order to verify part geometry. For example, we frequently hear that CAD is not available, not allowed to be shared, inaccurate, or incomplete. Sometimes, especially with legacy parts, the math data may not exist or may have been lost. It's common to use scanning in conjunction with reverse engineering software to rectify these issues. Structured like scanners, like the Artec Leo, project a grid of light onto the subject and then capture images of the scene with cameras. The distortion of the grid is used to calculate the underlying geometry of the object. Each capture frame is registered and compared to neighboring frames in real time to build a preview of the part on screen. With tethered scanners, this is just like the Artec Spider or EVA, this is displayed on your laptop screen or a PC monitor. With the handheld portable Artec Leo, this is displayed on the scanner's built-in touchscreen. Artec scanners do not require the use of tracking or alignment dots. Removing these tracking stickers from the process saves a significant amount of operator time and eliminates the risk of damaging parts and coatings. To maintain tracking, Artec scanners capture color information with every frame and use grayscale contrast to determine the position of subsequent frames. This is shown in the video on the right-hand side of your screen. Further, you will notice that every 10th frame is captured in full color. This texture can be wrapped around a completed mesh for rendering purposes, if desired. Depending on the scale of the parts you typically intend on scanning, different scanning solutions are available with appropriate technologies and 3D resolutions. For very small parts requiring extremely high resolutions, the Artec Micro, shown on the left of your screen, is a desktop automated capture cell. It finds frequent use in the electronics and jewelry industries. Handheld scanners include the Space Spider, the EVA, and the Leo, generally for small to medium parts. The Leo is uniquely portable in the scanning industry with onboard batteries and screens, allowing you to scan without a tethered laptop. Finally, the Ray, shown on the right of your screen, is a tripod-mounted LiDAR scanner designed for extremely large objects and area scanning. In the upcoming demonstration, we're going to be scanning a marine travel lift. We're interested in scanning only a single corner of the vehicle, not the entire lift. Based on that scan size, we've selected the Artec Leo. It's a high-resolution handheld scanner, which is designed for industry-leading portability. It has an onboard storage and file management system accessible via the touchscreen. It scans for 2 to 3 hours on a single charge, and the battery is field swappable, allowing for nearly continuous use. Files can be extracted from the Leo via microSD cards, a LAN connection using the onboard Ethernet socket, or using a Wi-Fi connection. As you'll see, no laptop or computer is required during the scanning process. This makes it ideal for complicated scanning environments like confined spaces or working at heights. It also functions perfectly in full sunlight, eliminating the need for complex lighting or a controlled environment. I traveled to a local yacht club to use the Artec 3D Leo to scan the marine travel lift. The Leo is excellent because it's a portable scanner. You can see that there's no laptop required. This allows easy movement around objects, underneath areas, and in confined spaces. I'm looking at the back of the Leo while scanning to visualize what's being captured. The screen on the back shows both the range of the objects being captured as well as the data density or data quality of what you're capturing. Based on the frame rate of the camera that this is recorded on, you're occasionally able to see flashes from the Leo. This is also shown as bright spots on the actual travel lift. This allows you to get a sense of what's being captured in every frame. Moving the Leo around the object allows for an easy capture of all of the interesting angles. The Leo can be held at various angles to capture inside some of the different gaps inside the travel lift. We're back at the office now, and it's time to post-process our scan data that we've captured with the Artec Leo and create a single mesh file from which we can begin our reverse engineering. We're looking at the traveler data now. It's been imported using the micro SD card on the bottom of the Leo. The first thing that we can do is delete any extraneous data that we're not interested in. In this case, I'm going to keep all the data that we have. Next, we're going to do something called global registration. The global registration program takes all of the scan data and reviews it against nearby data to make sure that there's no redundant data. Let's run that now. The global registration is now complete. For the 7 gigabytes of scan data that we have, the global registration took approximately 6 minutes. We can, at this point, run a noise reduction algorithm called outlier removal, but in reviewing the data, it's actually quite clean already, so there's no need to proceed with that step. Next in the line is the Sharp Fusion algorithm that will take all of the scan frames and generate a mesh file from it. For Sharp Fusion, we can adjust the resolution to whatever suits our needs. I'm going to use a 1mm resolution for this project. We can allow the Sharp Fusion algorithm to fill holes, either to generate a completely watertight mesh or based on a certain radius. I'm going to allow the Fusion to fill holes up to 3mm in radius. This will give us a good balance of a nice clean mesh without creating too much artificial geometry. We'll run that now. After 8 minutes, the Sharp Fusion has completed, and we're left with one tessellated model that's been calculated from all of the individual scans here. I've unloaded the scans from RAM just to save a little bit of space, and we can begin reviewing the actual data. Looks pretty good. We're left with good representations of the hydraulic lines. All the plates are showing up well. There's a couple of holes, but nothing that's going to stop us from fulfilling our reverse engineering work that we need to do. The next thing that we can do to make this a little bit easier to import into SOLIDWORKS is run a mesh simplification. We're going to do that using the shape deviation method and choosing a tolerance that we're comfortable with for our reverse engineering. I'm going to use 0.1mm. It's going to bring down our file size significantly, but won't affect the overall geometry too much. Let's start that now. Now that the mesh simplification is finished, the last thing we'd like to do before moving into SOLIDWORKS is move this mesh to a more useful coordinate system. We'll do that by first constructing some planes on the actual mesh data. We'll use this area here to define one plane, and we'll grab the front of the travel lift to define another. Excellent. Finally, we'll go into the precise positioning editing tool, and we'll align those planes with the origins. Great. We'll now save this as an STL file and export it. The next step of our process is going to be reverse engineering the scan data in SOLIDWORKS. To do that, we've imported it using a special import tool built into GeoMagick for SOLIDWORKS. This creates a data structure that can handle larger meshes and point clouds than SOLIDWORKS can natively. we can see that by taking the time to orient the scan data in Artec Studio, it's come in orthogonal to all of our normal coordinate planes. This will make it easier as we move forward through reverse engineering. The first thing that we can do is begin extracting useful geometry from the model. Let's begin by extracting a cylinder from the outside faces of the hub. We'll select a couple of areas. We can do this extraction making either solids or surfaces. We can choose to orient that cylinder to the world if we're confident that the axis of the cylinder should snap to one of the main coordinate planes. We can adjust the capping of the cylinder to determine how far it spreads, and if we know what the rotation axis should be, we can suggest it. In this case, we'd like to extract it just based on the geometry. Next, we can use planar extractions to create some of the other pieces of the weldment. We'll do that now. We'll begin by selecting this forward plane. And we can also select multiple areas to get a better result. The selection process in Geomagic for SOLIDWORKS is based on the curvature of the mesh. If the curvature is continuous, it's part of the original selection. For areas where there's more information or where you'd like a larger tolerance, you can move your cursor vertically on the screen, like this, to increase how much is selected. Finally, let's extract a cylinder from this area of the hub. Now that we've extracted a bunch of relevant information from the travel list scans, we'll hide them and begin our design process. We can always show these scans and return to the Geomagic for SOLIDWORKS plugin to extract any more interesting data. We'll begin by trimming some of these surfaces together. Okay, we've trimmed a bunch of the surfaces together. I did have to go back and grab 2 more surfaces from the scan model. So those were pulled from the original scan using the planar selection tool in Geomagic for SOLIDWORKS, pulling some of this surface and this surface. Now that we've got that simplified model of the lower leg of the travel lift, let's have a quick comparison and see how accurate we're doing. It's good to check this every once in a while just to make sure we're on the right track. We'll run that now. All right, so we're having a quick look at it. Anything in bright green is within the same space as the model within a 0.3 millimeters. So we're expecting most of the planar areas to be pretty good there. The cylinder is good as well. Areas where it's gray, there's no scan data for it to compare. That makes sense. And areas where we're seeing blue here, that's actually where the model is an I-beam, and we haven't bothered to model that in right now. We're modeling this as a rectangular prism instead. Now that we've constructed a block model of the rotating part of the travel lift leg, we can continue with the rest of our design. We'll be building some guarding around this tire. To start that, we'll build a bracket just above this flange. We'll create a reference plane on that flange. We'll make sure that that plane is snapped to the rest of the world. We'll create it. The next thing we can do is extract a cross section. The cross section will be driven by this plane. In this case, we'd like to be offset from that plane slightly. Let's call that 20 millimeters. 20 millimeters up. We'll fit that plane using lines and arcs only. It doesn't need to be a closed curve, and we'll limit the selection to this area here. To the cylinder, this piece, and this piece. Excellent. Let's have a look at what we've created here. We'll hide the travel lift. Let's hide out of all of our surfaces as well so we can have a good look. Excellent. So the next thing that we can do is complete the rest of this sketch. We'll edit that sketch. This needs to be trimmed together. This needs to be trimmed together as well. And finally, a couple of little gaps need to be filled. Okay, we'll use SOLIDWORKS built-in thin extrusion feature. In this case, we can do a 30 millimeter wide strip around that horseshoe, and we'll assume that it's going to be cut out of 3/8 inch material. All right, let's see how that looks on the travel lift. Great. Let's keep designing our fender. We'll offset the cylinder we had extracted around the tire, and then we'll extend that cylinder inwards and outwards a little bit so that it covers the full extent of the tire. Next, we'll create a normal SOLIDWORKS plane roughly parallel to the ground based on our existing axis system. We'll select a height that seems appropriate, and we'll use that to trim the cylinder that we created. We'll also fill in the inside surface. We can knit those two surfaces together and then thicken that to represent the sheet metal of the guarding. At that point, a very rough version of the fender has been created. All it needs now is to be attached. Now that we've finished the fender design, we can continue our design process by adding other features and completing the rest of the design process. This may or may not require additional information to be brought in and captured with the Geomagic for SOLIDWORKS plugin. In this case, we're doing a quick strap to join one piece of the fender to the welded leg of the travel lift. This can be done without the mesh data, so we've got it turned off for easy visibility. If at any point you'd like to verify any of this data against the scan, the visibility of the scan can be turned on and you can check again. That concludes my scanning and reverse engineering demonstration. In addition to hardware sales and software sales, Javelin is proud to offer scanning, reverse engineering, and inspection as part of our professional services group. Operating out of our Oakville, Ontario headquarters, services are a great way to leverage 3D scanning prior to full implementation. We offer drop-off service for smaller parts, as well as the opportunity to scan at your location with the appropriate scanner. We also process data and do reverse engineering to your needs. Thank you very much. Have a great day. Please let me know if you have any questions.